also that I will live stream on YouTube as well, so that we have your introduction recorded. Give me a second. We are going live. Okay. So now we're ready.
All right. Perfect. Well, so nice to see you guys firstly, and I apologize for not making it yesterday. There was a crazy COVID scare, but everything's good. So I'm Misri Patel. Nice to finally see you guys. And yeah, I'll be co-teaching this workshop with Sarah, who was the name giver for Bianco, and I was like a part-time caretaker of Bianco about 2 years back. And currently, I'm a research lead at the University of Michigan, and I'm lecturing at UPenn this summer. And yeah, I can't wait to jump in and get started and share the same Bianco enthusiasm with you for the next 5 days. And we also have Jeff joining us from the Bill Lab at Lawrence Tech University. So we'll have Emily and Nathan really sort of walking us through how it really is working with the robot in person, and hopefully we could run all your scripts in the Bill Lab, and also sort of do some recordings and live shots, so you can really see what you've been designing on your digital platforms in our physical space in Michigan. So firstly, I was just going through your submissions, and I would just commend you guys for the kind of work you've come up with. And with that, I think we should open up the floor and chat a little bit about how the first assignment treated you guys, or if you encountered some hiccups, if it worked, if it didn't work, and if so, why. So I guess if you guys have any comments from yesterday, we'd be, and since we're doing this on a digital platform, if at any point you have questions, just like throw in questions in the chat or raise your hands, and we just want to be sure to make this digital/physical process as seamless as we possibly can. And it's a challenge, but yeah, we're hopeful, and I hope likewise.
Yeah. So why don't you share your screen, Misri, or I'll pin you if you want to use OBS
Right
camera.
here. Okay. So with the first assignment, I think it was a good introduction to sort of introduce you guys to what a robot is and what it means for the robot to have 6 axes. In a lot of ways, even when I'm working with the robot, it's as simple as using your hand to sort of, really understand different positions, different axes it could play around with, and which I think your diagrams are, generally speaking, really playing with that idea so well that you can understand what is really doing in 3D space. What we'll be doing today would also sort of piggyback on our concepts from yesterday. The only difference would be that with this assignment, we were working in the XY plane, but using the same kind of logic, we'll also look at what the transition is like in the vertical plane, and we'll introduce, Sarah will introduce the next assignment. One thing I noticed was how we're still trying to sort of understand 3 main concepts. The fact that the robot starts with a home position, which is typically the start and end position. It could also be different, but it's also sort of good to see that it's really important to understand the points we're extracting, because if we break down a really really complex looking Grasshopper script. It's a fairly basic analogy of sort of extracting the points, and I mean, the robot cannot really do everything, right? It's a pretty dumb machine, so we have to feed it a lot of information, and I think your diagrams really sort of understand the concepts, especially this one. And I think we'll come back to that, and really, we'd like to hear your comments on these sort of diagrams to understand what the hiccups were. But in a lot of ways, it's also about using 2D curves and extracting certain points, and really feeding the robot with just enough information for it to run the script. And with that, I also think the same concept could really form seamlessly with the next assignment. So I would recommend you guys to sort of build on each day with what we're learning the previous day, and we'll sort of keep building blocks with the same kind of information. So with that said, let's open up to the audience and all the participants. We'd love to hear your thoughts on this, and also the graphic styles, because they're so it's a range of different styles of representation, different ways to communicate the toolpaths, and also sort of with the same goal of achieving this act of completing our maze. We're also seeing some funky toolpaths, and if you guys have any comments on that, I'd really, well, I don't want to be the villain here and call out names, but if we have Muhammad Almas, I hope I'm saying that
Hi.
correctly. If I'm not, please stop me.
Yeah, Mystery, you're right. But this is missing few things. Like I've added one video and some graphics as well along with that.
Mhm.
And here what I've tried to do is like, after seeing the maze, I like offsetted it and then populate few points. And then after measuring the tool's diameter, I just wanted to like create a maze within the maze to understand the flow, that how we can like maximize the movement of the robot. And just not that, after like finishing one path, you can see some decorative circles are also there. So after Z hop, like if we can like make a Z hop, and robot can like again go there and apply the second layer. So that was the whole idea. The video was there, but it is missing some. I don't know why.
No worries. Well, thanks for introducing that. And with this, it's also important to understand with the same start and end goal, we're also sort of dealing with different ways of doing the exact same thing, right?
Yeah.
Because there are no right or wrong answers. But my question to you would also be, are you guys sort of catching up with the kind of process that we're walking through? Because it's great that Grasshopper PRC, it's a very visual medium, but in a lot of ways, we're also trying to break it down into just key concepts of the fact that robot starts with a home position. It uses a point. Now, a point can have a number of planes, right? So we're trying to extract this information through Grasshopper, but we're also kind of using Kuka PRC to like stitch it together to almost form like a story with the machine. And what's interesting is with this toolpath, what we're really trying to do is extract just the information of its X and Y plane, because it's horizontal. But what we'll be diving into today would primarily revolve around the same idea, except the plane becomes vertical. So how do we use the same information to just extract certain planes from it and make a language out of it? So I would also, once Sarah introduces the next assignment, I would also recommend you guys to use the same kind of 2D curves and get and really rotate the planes in different axes to really understand where our in a lot of ways where our workforce comes in, transitioning from Rhino as the input curve, Grasshopper to sort of extract geometries, and then PRC sort of comes back in when we're trying to stitch a story with the tool pathing system. So it's great that you guys are getting a really good hang of
But I
the
have
possibility. Yes, go ahead.
one thing to say, Mesri. Thank you so much for the explanation. But the sixth slide, the slide that I have explained, is missing like few videos and images that I've already uploaded.
Okay.
But it's not there. It is showing how the robot is moving and stuff.
All right. Okay.
The
No,
moving
that's good to hear.
condition, the tool pattern.
Yeah, feel free to drop in more diagrams. If I mean,
Yeah.
are you having a
I have
hiccup with the
already uploaded that. I don't know
Oh,
why it
okay.
is not like
Oh, that's
showing it.
weird.
Yeah.
All right, we'll keep an eye out for the
But
changes.
yeah,
But
anyways, yeah.
perfect.
Thank you
Do
so
we
much.
have absolutely? Do we have anyone else uh, from our participants with
Hi,
thoughts? Yes.
hi. I'm Spartaco. Everything was yesterday perfectly clear for me. One thing that I missed is that I had to upload my version the of the file. So, but all of the question that came to my mind yesterday was perfectly explained by Sarah. So it it was all there. So it's great, awesome, guys.
Perfect. Okay, it's really helpful to know, or if at any point you think we could communicate better, or if using a different medium could help, just feel free to give feedback and stop us at any point. Um, just before we jump into today's assignment, I think this one question that I'm really interested in hearing answers about is it what you expected the robot to be? Because I think that's like the most, it bursts a lot of bubbles, yes, but it also sort of tells you about the possibilities of a robot, but also the limitations of it, because it has its own limitations in terms of extents, in terms of sizes, also in terms of, I mean, just the fact that we're using Bianco, which is, I mean, maybe this animation does a really good job of explaining that, is that essentially the robot, instead of doing a top down motion, it could have very easily gone the other way as well. And there are I mean, it's primarily used in automotive industry, where since the extents of your robot essentially lets you cover almost like a sphere, it could also go from underneath and do the exact same maze. So it's also good to keep an eye out for collisions, and we'll hear and learn more about it through the workshop days. But it's, even when you're, I think the great thing about using simulations is that you can literally do anything without running the script and still understand what collisions would be like, or what the possibilities of just the motion in general is. So yeah, let us know if you have any thoughts on that. But other than that, I think we're good to go, and we can kick off today's session.
And Misery, to me, it's funny that you're giving for granted that they know that the robot's name is Bianco, which it is
Really?
true that I mentioned that yesterday.
Did you not? Okay, I just talk about Bianco as like extended family.
It's so
So if I'm
funny.
obsessing over that, please stop me.
No, I love it.
All right. So
No, all great comments. Thanks, Misery.
you should start saying Bianco, because it's white and it's pretty. All right. Yeah.
That's true.
Let's get started.
And yeah, it was great to hear your comments since you hop in, you join us today, and so you're like, at first glance you're looking at their submissions that I think they look great, and hopefully you guys had fun, like finding that new ability to control that kind of representation. Thanks for the effort as well to record animations, to submit GIFs. I think that everything looked great, and just a technical thing I've noticed, like if you want to upload videos, feel free to do that also in the folder, in the like video demo folder, so that we know that everything is shared with everyone, and we know that we will have access because we have the possibility to get into that content. Yeah, so what's our idea today? We, as Misri mentioned, we would like to dive into this second assignment, which is called LightBright. And this assignment, we would like it, and actually I'll start sharing so that we can have some visual support here to the content. Share the screen. We really would like you guys to produce these images for your portfolio. We'll see how many students attendance will submit. We'll see our implementation time. We'll try to make it work before the end of the week so that you guys will have images and documentation of your outcomes. And given your start, we are really curious and excited about what comes next, and to see what you guys will produce, will realize. Yeah, so we will talk about this assignment, and then hopefully, like, we would like to find some time for a work session. And while you guys are working, I would like meanwhile to communicate with the Build Lab at Lawrence Tech Co-Ed, so that you can see the workflow in real time. While you guys are working, myself or Misri, we could play with Grasshopper and Kuka PRC, produce some very simple, scribbles, sketches in the air with the robot, and we can just submit, I don't know, the file, the CRC file, in the chat log, or like, Jeff, if you want the files, you let us know. But we can try this, and you can load the files in the robot, and we can see what happens. So that's so in here, just to begin with this presentation, you have a sense of what we would like to do, for you to make. We call this activity robot-like painting. It's a great way to understand what the robot does in space. And the more you understand robot programming and Kuka PRC and this kind of workflows, you can tweak some settings, and you really can see the differences between one kinematic mode and another, and you can see how to connect the target points. You understand how to interpolate the algorithm so that the motion gets more or less smooth. And it's just a very explicit way to visualize the invisible, something that it's actually not visible. And I would like to start with some precedents. For instance, in this case, they come from the 1914. This is a reference that Carl Dumman, the dean at LTU Co-Ed, uses a lot. And I've done more research on this. These are the motion studies from the Gilbreth, Frank and Lillian. A couple of engineers, Lillian Gilbreth, also a psychologist. They were pioneers of motion studies as it relates to production, to human production and human motion in assembly lines. And they were ergonomic experts as well, and consultants. So, when you see these images, basically it's an early stage version of what we're trying to do with the robot, meaning that they attached some lights to the wrist of people, like carrying out actions, and they depicted those actions through long exposure pictures to see really the sequences, and with the goal of optimizing these sequences. Of course, now if we look at these things, this study might have a dark side, like the complete exploitation of humans And we can have, of course, a conversation about that. And by the way, you guys feel free, and Misri as well, and Jeff, to hop in the conversation whenever you want. But it's just interesting to see how these studies were deployed in many sectors related to human motion, human tasks, also translated to, I would say, architecture / building construction. This is an example, and I dropped here. You can find it in the slides, the link to some videos of the Gilbert studies, in which they depicted basically the activity of bricklaying. So workers on site, building stuff, and really studying their motions or pick and place of a brick to build something, right? And they were very, very analytical. And so, like, as you can see, they tried to track how intuitively a person could do to accomplish this task from start to end, and pick a brick and lay it and see what happens. And so they really counted, motions per brick per hour, and what happens by the end of the day, and how can we optimize it. And so they suggested ways in which a human could pick with the optimized motions the object to be used for construction. And then again, I mentioned some of these things yesterday related to when we have new technologies, we want to understand them, and we want to use them as analytical tool, as tools of analysis to understand more in depth the reality, and in this case, production. More of this, we are in those years. Well, I didn't mention that Lillian Gilbert broke many standards for the time. She was the first engineer, first female having PhD in engineering to have a couple of degrees and so on. So she's a hero to me. But moving on, more of this, more or less same years when John Milley, hopefully I'm pronouncing this in the right way, American photographer, Albanian origins, close friend to Harold Edgerton, who was a professor at MIT, who basically was not saying inventing the stroboscope, but a version of this, making it just entering the market. So that this tool wasn't used anymore only for scientific research. So basically, this organization are very smart and smart people that wanted to pioneer new ways of investigating reality, coming together and sort of linking these technologies to art. So this is an example of Pablo Picasso. You might have seen some images like this of Picasso painting in space, in the three-dimensional space, and this activity depicted with long exposure pictures. This actually was inspiration for a group of students a couple of years ago that basically created the same drawing, the same atmosphere, the same mood, also with the robotics, using Bianco to create this geometry in space. More inspirations. This is the work of a digital artist that wanted to sort of depict Shakespeare poems with lines. So basically translating poetry into an algorithm. And he's finding here rules to analyze each line, basically, and then putting in a sort of XY graph for each line, the amount of words and the average. So number of words divided by the whole count. And so basically with this relationship, you could just drop a dot in space and then interpolate the dots with a polyline and connecting them and creating a geometry. So in this way, you have sort of this kind of analysis depicted in a visual way with this visual approach, let's say. And it was, and we can talk more about algorithms and relationships. I think that you guys had the sense with the previous submission on what it means to create relationships and what it means to put them together and to tie them together so that at the end you can have a robot motion. And that was just an inspiration, you know, to start testing some things, to look at what the Bianco could do, to look at opportunities, you know, to express creativity in this way as well. As I told you, Bianco has, and Misri mentioned that as well, we have to look at limitations as well of our tool. I told you that Bianco comes from the 90s, so not necessarily we'll be able to create geometries disarticulated, only because we have just the limitations of line that we can use. I'll talk more about this later, but like these are other examples. Maybe Misery, you might know Christopher from Michigan, having fun here with some like painting, different colors. I think that I've seen many other examples like this, also using a strobo light and having sort of a dashed line as a result at the end. Very sophisticated outcome in this case. So like while I'm talking, guys, keep thinking about the geometry, right? That you would like to accomplish, that you would like to see in space, and that you would like, you know, Bianco to try to accomplish it. Just opening a parenthesis, Misri mentioned this before. Think also about your final idea for the final submission, what you would like the robot to do. Misri, you said that Bianco is them. Oh, come on, don't insult poor
What?
Bianco. You said that Bianco is them.
Oh no,
No, it's
I
dumb.
just said
No, it's
robots are
dumb. Are dumb. Don't insult my robot.
because no, I have a really soft corner for Bianco, but it's good to sort of challenge ourselves because with AI picking up so much, and we're all into like sci-fi movies, that it's so easy to assume that it can do anything. Of course, it could potentially do anything as long as we give it all the alphabets and words to make a sentence out of it. So in a lot of ways, it bursts our bubbles, but that also means we can really program really intricate details about the motions, what the end effector does. That's essentially the tool that goes at the end of the robot on the 6th axis, and also sort of opens up new doors to not just use the robot as a machine, but also the end effector is a tool in itself. And it can start from really simple manual chores to really sophisticated tools like the ones you may have seen in like automotive industries, where all one specific robot does on the assembly line is weld all day, but they're really sophisticated tools. And so the robot isn't, in a lot of ways, it's an arm, but what you hold at the end of the arm really changes the game in a lot of ways, and also gives you an extra level of flexibility. I think recently I came across another project that essentially had a robot on top of a robot. I don't know why people would do that, or it's just an experiment, but it's also interesting to see that when you have a robot with 6 axes, if you were to add another one on top of it, that just multiplies it exponentially. So it's interesting to see, and of course, we'd love to share more examples from contemporary research practices, because especially with this technology, which is so which just intuitively comes to production methods and car productions, or just industrial ways and industrial ways of making, that looking at it through the lens of architecture, or like through the lens of a designer, really sort of opens up new possibilities, and also looks at it with it becoming a potential tool for us. So I don't know if all of you are architects. Can we take a quick, I mean, what's your background like? Are you all into architecture or designers or industrial designers or engineers? Or I'm just at this point assuming everyone's an architect, but if you're not, please feel free to share insights from your background as well.
There's a little bit of everything, I think. Architecture, engineering, urban planning, urban design, archaeology, minor, nice.
Nice.
Design, communication, art. So yeah, but like architecture is the fil rouge connecting them. So
Sounds good.
yeah, I think that we are understanding the terminology and, you know, like those connections that you are mentioning. Yeah, and it's a good point. You mentioned the robot on a robot. Why people are doing it? Because we can, Misery, come on.
Right. Why stop? Why stop movies?
No, but it is interesting because like other companies are developing, and especially in, well, of course, like big tech companies, but also in medicine and surgery, there's like big level of advancement of this kind of tools when you can see like the robot having like 10 arms, like the 6th arm actually like becomes like way, like you can multiply it and to have all a range of end effectors that can be smart themselves. Like those objects actually can become smart when we augment them with other tools and computer vision systems and so on. So absolutely. And for like in this week, in this context, we won't have time for you guys to add authorship to the process, but just wanted to share anyway an example with students here that designed a tool and then the factor so that the robot could interact with materiality, could understand double curved surfaces, and could draw lines and following the perpendicular of like the target point basically in space. And this was actually an in-between exercise between the LightBright and the hot wire cutting. So it's like, it's not yet crafting material, but it's touching it. It's sort of like getting a closer relationship with the physical world. Here, more examples. That's submission. Maybe about it. Yeah, FT submitted this past spring. Great image, great interpretation of the assignment, and we should have a demo as well. At this point, I'm asking Jeff or Emily if you guys want to add on this while I'm playing the video that you recorded. Or anyway, usually we, you know, in the lab, we switch off the lights. As you can see, the end effector has a small LED light attached, and we take the long exposure picture. In this case, to see the demo, to see what's going on more clearly, we recorded this video with the lights on. I'm trying to expand the slides. And here, sort of a hybridization of this documentation for you guys to really to see what's going on with the kinematic and with the potential final result. The model is not accurate. Sorry, I'll finish and then I'll give you the word, Jeff. It's not accurate 100% just because video and pictures were taken in 2 different moments, but so that you can have a sense more or less of what's going on. Sorry, Jeff, I interrupted you.
No, I was just going to say that's super cool. I like the composite. One thing I want to note is that for the LightBright, like 3-dimensional motions, both toward and away from the camera, tend to yield both better scripts and better photographs. I think it's because when you're dealing with like a 2-dimensional thing, like as if the maze were flipped upright, then the robot is working in a two-dimensional plane just facing you, right? But due to the way that the 6 axes work together, we found that was more likely to produce, I guess it's called a singularity, where 2 axes need to rotate against one another in order to maintain constant motion in that plane. And so, you know, I would personally encourage like a 3-dimensional LightBright interpretation to get the most fluid motions out of the assignment.
And also there should be an opportunity really to create something in space. So there's a technical issue related to that. So like, don't create a geometry that it's flat, but also really try to exploit the potentials. So
yeah, I wasn't trying to say it should be a limitation. I was just saying, think in 3 dimensions is a great, you know.
Exactly.
It's new and different from the maze.
Right. Exactly, and really try to imagine something that occupies the space, the 3D. Misri, wanted to add on it?
Yeah, actually, that's a great point, simply because not just in terms of its technical sort of, or like streamlining that workflow, but what giving it depth also gives you the chance to have higher intensity or sort of going back in space, and that adds a whole different quality to the final image itself. And we'll see a few examples right there, which, like on the top surface, you see that the lines seem to be slightly more thicker than they are, and towards the bottom they tend to sort of become slightly thinner. What's interesting to note is that the LED is a constant, and the motion path, just adding depth to it, sort of gives you that ability to also sort of share this idea of perspectives. Of course, it's at a much smaller scale, but you could also use this to your advantage to you know, really add more flesh to a simple toolpath.
Yeah, absolutely. Well, great comments. So guys, try to take all these suggestions under consideration while you're thinking about the exercise. So let's get into this. What we are asking is to use the light as a tool to visualize the kinematic of the robot. We'll try to make it happen in reality. We'll take a long exposure photo of your script that you will submit. We're asking you to create one geometry and to export the script. And please to submit also Rhino and Grasshopper files, because in case there are hiccups, we can manage that, and we can tweak your files and make everything run smoothly. So so we are asking, so the task is to create an abstract geometry that you will translate into a robot toolpath. You know how to do that, but we'll talk about, we will show a demo in a second. So please submit as you did for the previous submission, the documentation of the process. You can document the toolpath, you can represent the robot going through the toolpath. It's really your choice how you want it to represent your work. Use diagrams, really use your creativity, like in Google Slides, but also please submit the files in the Google Drive folder so that we can double check them and you can make the process faster for implementation by the build lab. So we have put the deadline at 3 p.m. today Eastern time, tonight in Europe, etc. I would say just as soon as possible, in a way that we can have your material and we can start processing that. So that's the intention. That's the reason why we are trying to push the, you know, the timeline. Yesterday you missed where we can or have to upload our tests. I'll show that, no problems. Meanwhile, just a slideshow of some interesting images that were realized by the students. You see, like, three-dimensionally, see like this sort of outcome in the space. More of this using the loop. It's not mandatory, but if you guys want, you can install an Imony plugin for Grasshopper that allows for the creation of loops. And I'll in the demo, I'll show you guys how to use it. I think it's interesting because with one simple, start initial geometry, you can create sort of an interesting loop, an interesting repetition of this geometry with some variations. I think that just the creation of the rule, it's an interesting aspect to learn. More of this with some documentation as well. Emily, this is an image from Emily from this past spring, both representation of the robot and the toolpath with the long exposure images. And here a bit of we won't have, just because of the tight schedule of the workshop, we won't have time to analyze what it means to produce two kinematics in point-to-point and linear mode. But we can show you with images, with some outcomes from this past semester, what it means in terms of, I think you can have a sense of where the target points are here and how we are connecting them, either through a linear path, so just like a line that connects the points, or the point-to-point movement in which we have more room for interpolation. And so in this case, you see this kinematic like going more, just visualize more smoothly, right? And you can decide how you want to export that, depending on the geometry that you have in mind, if it's more or less curvilinear. But please export one, and we'll see if we have more time. We can try to take more pictures, but let's go from this. Let's start from this. Another example. Again, like, it's a great analysis tool, really to understand what's going on in space and how you can tweak the settings and how you can achieve different results. So in this case, we're seeing really the robot moving in space. Just imagine, as the Gilbert did with humans, how you would like to optimize the toolpath and optimize the robot motion, especially if you want to produce something. So deal with materiality and, craft the material, and whether we're talking about subtractive process or additive process or outward cutting. But yeah, you have room for really for customization in all senses, like both the design, but also the toolpath, the settings, and so on. That's it. In the folder, you should see, you should be able to download the files for today's demo. This is a loop, actually. We'll go through this. And as usual, you'll be able to visualize, the script, but also the representation of the robot's axis. I've dropped some videos. I don't know if they have sound, doesn't really matter. Just you know already how how to visualize a digital twin, how to show certain things. In this case, that's the image that we were describing earlier. And so, like, with these Cartesian views, you have more clearly the idea of where the target points are compared to the robot, how far they are, how close they are to it, to the origin, and just really take this opportunity to work as much as possible in the 3D space and try to see what happens with lights, and try to see, as Misri mentioned before, the thickness of the lines, where you think the robot slowed down a bit or went faster, and depending on the way you're exporting the script, the toolpath. More examples. These are not animations, images, again, after the possible documentation. That's very minimal. You decide how you want to show the geometry that you're proposing for this exercise. More examples, also in the 3D space. This is a bit flat, so I would encourage you guys to work more in a way that you can really variate the target points in X, Y, and Z.
I have a question for the
Yeah.
test. The tool that we will use on the top of the robot, that will be a nothing, or that will be a light that is a point, what it is.
Oh yeah, that's a good point. Let's see if even the previous slides is more clear. So well, that was the end of the presentation, and I'll zoom in a little bit more, but maybe in the robot working in real time, it's more clear. We'll go into that again. So as you can see, like oh, thanks, Jeff. Thank you, Jeff. So Jeff is showing it in real time. So basically, we 3D printed all the end effectors, well, almost all the end effectors, but the hotwire cutter, because it's more articulated tool. But the others, we 3D printed them. So you can see like just the platform, the base to be attached to the arm, and then we just screw that, attach that to the robot's head, and yeah, we just inserted an LED light. Very simple, low engineered end effector, and that you will find it in the Rhino file. We modeled that for you. You will find that there. Did I cover everything? Misery, Jeff, Emily?
Yes, absolutely. And thanks, Espartaco. Am I saying that correctly?
Yes, yes.
All right.
Espartaco.
Espartaco. Okay, getting better. Okay. Oh, perfect.
I love your
Actually,
background. There's a lot of cool stuff there, Espartaco.
Where I'm an architect, but I have a little design studio on my own that we use digital fabrication tools for making things like some furniture, some lighting. Up here on my screen, I have some lights that we have designed, but it's awesome, guys. What you made with the robot, because I have a little approach here with a standard 3D printing, with my laser cutter. I made recently like a pen plotter. I use them. I attach a Sharpie to make a little drawing with the Sharpie, but this is awesome. This robot can take a design process of digital fabrication to the next step. So that is the reason why I'm here with you guys.
I wanted to mention this, like, so robots are the next step in your firm. So that's really awesome. That's really awesome. Thanks for sharing. And actually, I'm responding to your question. If you should have access to the workshops folder. We have divided the activities day by day. And if you open day two folder, you'll find the base files that you can download, both like the Simber file or the script with Anemone plugin being used. Submission files for you guys, please, to submit and find a way so that we can recognize like your name, like the author. Just name them in a way that we can understand who submitted. And in here, you'll find the slides that we've just been through, and the template in which we're asking you to draw documentation of the process. There are some blank slides here. You should all be editors, and just start the documentation here, and we'll discuss tomorrow. So basically, that's the organization, the daily organization. We start with some feedback of the previous submission, and then we keep going with the work. Does that make sense, Spartago? Yeah, is that
all right?
clear?
Sorry, but where are the submissions from yesterday?
And day one, and you can find the description of the submission,
But
requirements, and the template. Right.
Our work where we have to upload it.
Yeah, we are not asking for the day one. We are not asking Rhino and Grasshopper.
All right.
Yeah, because it's gonna be the same, pretty much the same for everyone.
Sorry,
so
but Miss Ree showed before some students' work, so I confused.
Oh yeah, that was the same.
Yeah. Yeah, sorry, I'm reading the chat. Yeah, yes, or Jeff, it's up to you. I can send to you anything you need, or just the script through the chat. We'll see how it goes. Let's do the demo first, and then we decide how to do it. That does it work? Okay, fine. So, and in this case, so if some of you are still confused, I'm just sharing the link with the that you can use to reach the submissions from the previous session. So submission template is where you guys are dropping the material. Are we ready for the demo? Yeah? Okay. Okay, so how about, Misery, what do you want me to do? I have with or without.
Yes, this is actually a really good primer. So I guess this is like yesterday, maybe we could walk them through like the three components, which is primarily starting from its home position and ending with its home position. But what we're really doing in the center is making a curve and extracting and dividing certain points and in a way sort of extracting the plane. So it's almost like a simple 3-step process with this exercise particularly. And I would definitely suggest sort of keeping an eye out for what you see right here. Let me just, whatever is going on right there with all the axes sort of marked out, because that's the most important thing to sort of note here. And yeah, that's actually pretty much it. And even through the course, when we're walking you through the scripts and while you're trying it on your own, if you have any questions, just let us know. So if it would help, we could also, once the exercises start to get slightly more complex, we could also jump into breakout rooms and, you know, really converse about your specific files. But yeah, that's our typical process for the next 5 days.
Exactly. And you guys can start working, start thinking while we're showing some of these things. So I'll start with this file. And let us know if you had issues with the download or anything not loading correctly. So I'll show the simulation, the virtual simulation first, because I want to say something about this. So for instance, now you see basically the robot always facing this direction, right? There should be also a more sophisticated way, to orient these planes. The problem is that we had just issues with the robot reading the script. So the initial script for this assignment was basically based on all these planes oriented toward one point, and that in our mind was the camera. So you could see all the vectors converging toward a point. The thing is, we confused the robot, so that's why we had to simplify it. And in a way, it's also good in terms of you guys did the amazing the maze ink assignment. And you know, and that's basically exactly the same script pretty much, except that we do not have the rotation of the tool that we discussed yesterday, if you remember, in the of like negative 90 degrees. So that's just something that I wanted to mention. In this case, as you can see, we have a geometry in space. I can mute for a second the robot, right? And we have really like these few steps. We will divide the polyline or the spline or whatever we want to draw in space. And because there will be a sort of version of, you know, approximation of the robot toolpath, we can increase the amount of points just to make the toolpath closer to what we have in mind, right? So it's just the division, the number of points that we are dividing, that we're using to divide our initial curve. So basically, it's pretty much the same script. We have to turn the points into a plane. So we need to, you know, to give to the points X, Y, and Z directions to understand where the positives are, positive X and Y and Z, compared to the world, if you remember. And then it's up to you if you want to try and see what happens when you plug either a linear move or a point-to-point movement. Quick recap: linear, connecting with the line, the target points. Point-to-point, doesn't really matter the shape for the robot, just connecting the points, the target points, to be reached in the fastest way possible. So going back to the tool, let's mute a bunch of things here. I'll mute, what else we have? The stage and the robot. That's the geometry of the end effector. It's this guy, so that you can see the 3D printed part and then the LED light just inserted. So there's just anything else. It's very low engineered. There's just friction keeping the light into like the 3D printed sort of attachment for the robot. As you remember, it goes on the origin. So in this way, we could have it showing up here. If I unplug it, this guy will disappear. That's just the neutral robot with no customization, no end effector, but we want to see it, to see what's going on. In this case, the end effector is shorter. Do remember, units are in millimeters. I reopen the tool settings, and this object along the Z vector is more or less 70 millimeters, meaning 7 centimeters. In this case, it's tool number 2. You remember the teach pendant, we have to plug these numbers as well in there. And in this case, just plugging 2 and then not changing the values of any rotation or any translation. We just have to tell the robot that, you know, this X, Y, and Z vectors the Misery was highlighting a second ago, they go here. This is actually the point that will match with our target point in space related to our geometry. I'm not moving anything while you're doing this. Perfect. There we go.
There we go.
Are you doing that with the mouse?
Yes.
Oh, wow. That's a skill.
That's not number 2. That's number 7. Sorry.
70 millimeters. Yeah. And Misery, what do you think in inches or in imperial or in
metric? Metric.
Oh,
it's,
awesome.
It's the units with like gallons and pounds, and I was like, let's just go back to kgs. Not a big problem.
Yeah, now I'm having issues like translating from millimeters to centimeters because just inches and feet get me so confused.
I completely agree.
So we go. So that's it. Let's go to the other file. Similar.
Oh, while we're here, I just have a quick comment about even when you see the relationship of the curve in how close or far the space from the robot, you're gonna, if this simply moved a little ahead, further away from the robot, you would also start to be more sort of conscious of what the work envelope of the robot is, because we could also share a few diagrams, but essentially a robot has certain sort of spheres that it can get to once all the axes are sort of when, or let me see if this can do justice. So as we all know, it has 6 axes, but for it to really get to
Let me zoom out so it's easier. Okay, let's put it there in space so you can track.
So as we all know, the robot has about 6 axes, and so if this was your simple arm, there is almost always this envelope of what point it can get to in space. So if you start sort of toggling your geometries, which at this instance sort of lies in a very sweet spot where all of the points are accessible by the robot, that's when your final Kuka component is gray and everything's good. As soon as you sort of take it further away, you're gonna see it turn red. And if that happens, don't be scared. It's just that the extents of the robot cannot actually get to your curve. So that's not to look at it as a limitation, but it's also good to be mindful of how far you can get or how big your geometry can be, which in a lot of ways sort of gives us a good reality check about the dimensions. Of course, there are a lot of robots, and each robot has its own sort of a sphere, like an imaginary sphere around it, which we call the work envelope, which essentially points out all the points it can get to as long as all these axes are, really just like spread out. So that would simply give you, this is just a quick visual representation of how far you can get with the robot. So just to sort of be mindful of that.
I have a question, Masri. So the thing is, this robot is having 6 arms, right?
That's
so
right.
To reach to one point, there can be 6 possibilities, right? 6 arms can
not
move
even
like
6 possibilities. It can have n number of possibilities just to get to a singular
same
point. It's just exactly.
Yeah, so can we like define its trajectory and like move different positional system of the robot?
You could potentially do that. That also involves a lot of extra steps in terms of because then you're feeding all the information about how much you want each of these axes to move, right? So as you have all of these, as I'm labeling them, 4, 5, and 6 are pretty close, but that also means you have to give it extra information about every step
The
in
particular,
reality. Exactly.
Yeah. Great. So,
So
it's
for,
like
yeah, go ahead.
fixed for like the pre-algorithm that is in there, according to which it is deciding the movement of the, like how to reach to the particular plane. But if you want to manipulate it, you can. You need to feed in some more information.
Exactly. So for the sake of optimization, what we are going to be doing here is, if we input a 2D curve which has all these control points, we're asking the robot to get to this point. Now, how it does it in the most effective way is what PRC is helping us with. So that's where we're sort of jumping from Grasshopper to actually extract all this information, and then we're sort of leaning on PRC to give us this motion, if that makes sense.
Right. Yeah. Thank you so much.
Absolutely.
I wasn't able to unmute. Do you want to articulate the node that you just shared?
In previous workshops in the Kuka PRC settings, under the screen there we are. No, that's not it. Is it in advanced? Whoever's got the screen right now.
Analysis, you mean?
No, it's where we want to set the start and end points.
Sorry, advanced?
Advanced. Yesterday you showed how to start to set the start and end position with the buttons just below the diagram there. So you see the picture in the Kuka PRC window of the robot and all of the axes, and there are buttons for get current position for start and end. So if you are trying to define the start and end point of the robot kind of well working in Grasshopper by using those buttons, if you click on those buttons, and I'm not sure if it'll do it right now. Let's try. Can you click on start? There we go. So note that at the bottom of the column of values for start, we see NAN entered for E1 through E4. Those are values for the end effector, and we have a passive end effector. So in this case, the light is always on. And so we just need to enter 0 for all of those values. Otherwise, it will produce an error message when actually running the robot. So that's what I was sharing with everyone. Finally found that yesterday, what the cause of that was.
Because we were looking at line 16, right?
Yeah, it's stuff that folks won't see. In there, line 16 of don't count the spaces. It's going to be start PTP start position. You're on it right there. So that I think is line 16 right there.
Is this one?
Or maybe it's
well,
in
okay.
any case.
I mean, you could find it anyway in the teach pen and the line. So the arrow gave an error on line 16.
Yeah, the teach pendant gave us an error message and indicated the position in the code where the error occurred, and so that's how we were able to find it. But this was the cause, and we finally found that too. So that's all I wanted to say.
That sounds great. Thanks so much. That will save some time. So great. So put manually these values here and then hit apply. And we don't really need that now. I don't know if I did it already. Okay, no, it's fine. So if you're interested in loops, and again, you guys hop in the conversation, interrupt me if you have questions. In this case, we are starting with the base geometry. As you can see, when we have Kuka PRC on with the toolpath visualization on, we see sort of like the work in progress of the toolpath. So the more the robot advances, the more you can see sort of like the completed section, the completed part of the toolpath. So let's go back home. And let's try to see what happens when we use loops. For some reason, yesterday this option didn't work, but Control-Alt, you click on the component, you can find the loop component. We want to give you information, to feed with information this stream of loops, basically. So what we're doing, we're entering our geometry as data, and then we want to try something. For instance, let's explode it so that in a way we can have the vertices and the segments of this base geometry. And let's find a point on curve wherever you want. It could be in the middle, could be slightly shifted from the corner. And then let's connect these new points that we have found. And we close as well the polyline, because usually by default, this will be an open line. So once we have this rule, so we have set this rule for the creation of the loop, we enter it in the loop. And basically what's happening, and I can mute the robot for a second, you are creating a repetition of this rule as many times as you want, right? I've said 10 just because I think it's fair enough. It's fairly complex. And in this case, if we want to use the opportunity, to deploy the opportunity to use the 3D space, let's mute everything here and let's go back. So you have this chunk of script here available in the demo file. So same process, but this time, once we have the polyline, the new polyline that we have created with this relationship of points, we move it in space. We can move it along your own customized vector, or we can start with our X, Y, and Z. Having in mind, basically, sorry, I was rotating, where the positive is of each vectors. So in this case, you can plug really whatever you want, the X, Y, and the Z. In this case, I plug the Z because if you look at the work coordinate system, the positive X will push away from the robot, the visualization of your loop, right? So in this case, instead of plugging our polyline as input data in the loop end, we want to plug the result of our move component. And what we'll see is again the result of your iterations. If we start with 1, is basically, like these already produced one result. We have already moved this result, and then the result of the iteration will end up with this consecutive polyline. We want to use, again, I don't know, 8, 9, 10. We'll have these elements with these rotations that we have characterized. As you can see, if I click on it, I'll have only, the outcomes, the results of the script of the calculation of the loop. So if we use the merge, we can include the initial, the start geometry as well. Let's see it, and let's mute this one. And if you want to have a sense of how like this object will look like as a loft, you can check it out here and bake in it, right? So let's mute it, and we can even just mute the iso curves. So this is what we are creating, and so this will be this time our input for the process that you guys know already. So what we want to do is to take these curves, to divide them, to find the target points. In this case, as usual, you know that you could add points, but in this case, we don't have a curvilinear geometry as I showed in the previous demo. So there's not much need for approximation here. So you want to reach you want the robot to reach the target points, the corner points of this geometry. And again, we turn them into planes. We give them an X, Y, and Z definition, and then we plug it, for instance, in a linear command. So by default, you will have this kind of default, this kind of result. We can, I don't know, get rid of this for a second, right? So if you notice here as input, we have a dashed line because the robot is understanding each geometry, each line individually. Right? If you look at the list, we see basically the lines treated individually, and you can see 6 items before the hexagon as 6 lines, 6 segments, so 0 plus 5, etc. So we want instead the robot to operate in a system in which these geometries work as a whole. And to do that, we have to flatten this list. So we flatten it. We create, actually, let's do this so that you can see what's going on. I flatten. I have one straight list of data, of points. And as you can see, we don't have any more a dashed line here. And so the robot will connect now. Should we mute the points? Maybe yes, for the visualization. Or we can see the planes, and then you can see where how all these lines are connected. And as we showed yesterday in the last live session, we can do, if you want to have control over what's going on, you can start seeing, you know, where's the start point for each geometry. And actually, you might have a sense here of the fact that 5 and 0 are connected. So the robot will stop here, the kinematic, and will start the following one, starting from the, here, the initial point of the following curve. Does it make sense, guys? Okay. And yeah, so the process doesn't change. So Jeff, are we brave enough to export this and to give it to you? Also, what I can do actually is to remove this initial line. Yeah, tell me,
Let's give it a
Jeff.
try. Why don't you drop it in the chat, I guess, the SRC file.
Perfect. So let's do this. So I'll put, as you mentioned, is this close enough to the 0? Let's do here. Let's put this as a start position. Did I do that? Yeah. And what you want me to do to put 0, 0, 0 here?
Yes, please.
Oh, absolutely. I apply. Let's run a simulation to see what's going on.
You need to take the spring off because the spring is going to point downward. Because it has a different definition.
Everything.
Let's leave the spring down.
Everything is fine. There's no red areas, no singularities. Okay, let's try it. Stop.
The main, the light. She did. All right, let's take that off.
One additional comment in here. You know, you sort of have to speak machine. You have to understand the robot's language. So when you name this file, don't put symbols, don't put numbers, just keep it simple so that the machine won't get confused. We apply this, and I have, I would like to show you the file here. Let's see, sorry. Okay, and let's see what's going on. I'm sending this to the chat. And I would say we could start the work session. 8 characters or less, all lowercase, no numbers are open. Jeff, now you know by heart how to troubleshoot everything. Yeah, that's great.
There are certain words are disallowed too. I don't know the full list, but words which may overlap with commands, such as test, is also a disallowed file name. I don't know the full list of words, but.
Great, thanks. So let's do this. When you guys are ready, I'll pin your video so that they can see what's going on in the build lab. Does it work?
Sounds good. I got the file.
Perfect. Awesome. So thanks a lot. So let's just be here connected with the build lab. You guys start working. Meanwhile, so that's my idea. Misri, you tell me if that's okay. I would like to.
Perfect.
Oh, here we go. For those that don't know what the floppy disk drive is, here we go. That's the object that we're using to transfer this file that we just sent to the build lab through the chat log. So Misri, my idea now is to create real quick squiggle like a version of this to see how to do it. And then if you want, you can, and then I can send this file as well in the chat. And if you want, you can create one, or I can just keep going, keep talking.
Sure. Yeah.
Okay.
While we're at it, I see that the presentation had one of the images from Christopher with the LED images, and I think just to decode that a little bit, or maybe we can talk about it later. But the only difference essentially between what he was doing and what we're doing is we have like a single light source right there. Oops.
True. Oh, sorry, I was going to the presentation, but yeah,
that
I'm
would be
staying
super
here.
helpful. Okay.
Okay, let me go there. Let me go there then. It's here, submission, precedence.
All right. So what you see on this image right here is essentially the tool at the end of the robot is a point source, right? So like we saw, it was something like that with 1 point right here. And the only difference, so even the kind of tool pathing is almost exactly the same, except what he was doing here was, instead of a point, they had like this strip of LEDs where it's basically 1 point for each sort of color on both sides. So in reality, all you're seeing is like something like that here and something like that on the other side with a strip of LED. And the toolpath in a way sort of becomes like a simple circular system which has like 2 crossed loops. So in a lot of ways, I think as we progress through the workshops, we can also sort of look at images and think backwards about what the tool could have potentially been, just to sort of decode the entire process in like a backward fashion. So that's literally the only difference between image 1 and image 2. But
Awesome.
yeah, I think
Is this the overall toolpath, like the third image?
this one was,
because I
I
think he has too many points for Bianco, that one.
Yeah, I think the file was really heavy and they took quite a bit of time to, really get to like really intricate geometries, because at some point you see a lot of information being flooded, which could take at least like 30 minutes or so to run a toolpath and, generate one good image. So yeah, these are like the main key differences between all the 3 images that you see in front of you.
Yeah, that sounds great. And yeah, so Jeff, the next step is to have tool and the factor with multiple LED lights for your information.
Okay, so I made one that blinks and has an adjustable LED. It's on breadboard still. So got that. Would you share the file with me again? I made the mistake of downloading it from the chat directly to the floppy disk. And now when I try to download it again, it looks for it on the floppy disk. Could you just share that with me again, maybe in just a direct message?
Sure.
Thank you.
Does it work like this? Fine. Okay.
Just going to the desktop this time.
Okay, let us know. And
yeah, it seems to be working fine. So just downloading that to the desktop and then to the floppy might be helpful.
You're muted, Jeff. I know.
It was the robot that was objecting. I got the file. I'm not sure what the formatting difference is.
Okay, well, careful because the L2 computers are overly protected. So you might need to sort of unblock or something the script that you just received. And if you could then like bring the computer close to the robot, that would be awesome. Awesome, thanks a lot. So we have 30 minutes. You guys use this time to be productive. Meanwhile, why don't we do a scribble? Really, let me add the stage so that we have a bit of reference. Sorry. And by the way, you guys, do you feel that you have questions or everything is clear so far? Yeah, no questions. Let us know. Let's do something real quick.
Also, at this point, we're assuming you know how to export. I mean, since the GIFs and all the videos and diagrams look great, but you could also bake the robot at certain points and extract the 2D curves, take it to Photoshop, Illustrator, either way, and you know to sort of add line weights or to sort of make more diagrams as we get to complex processes. But I guess you guys have a really good handle on that already.
I don't know what I've done. I moved the I moved the end effector.
Just lock that.
Where is it? Here we go. So you have this guy as well. Pretty are manageable actually, but the meshes are pretty articulated. Leave it there. So that's the fast way to create a squiggle there in the space. Usually I use the component Populate 3D. I plug my region, right click, set one geometry, and I plug it there. And then you have sort of the preset count, which is 100, preset seed 1, and the point. There's no reference to a point that it works as a seed. Let's hide this for a second. Okay, so we have the region, we have the points. Let's say that we want to plug a slider that goes from 1 to 100. And I drop that. So the Bianco, so one script should be maximum 700 lines. So try to stay in that range. Lines including, you know, all the information needed at the beginning, like included the start point, the end point. So don't exaggerate too much here with the amount of points. We can change the seed. You can randomize the seed. Let's just plug a number at the moment. Just if you are not aware of this, you know that with the double slash, you can plug directly a panel with a number. Whenever you want to plug a parameter that doesn't change, that's not a slider. So we have this. We can visualize some variations. Let's do, I don't know, let's do 20. That's fair enough. And then let's hide the geometry, and then we can interpolate the curve, and we plot the vertices. And then we have this. So if we hide the points as well, you could really look at how to create a range of geometries given your input data. We can even simplify it. Okay, so Misri, you say stop.
All right, that looks great. The previous one. It resembles like number? One. That's the one. 2021.
This one? Mm-hmm. Okay, let's put it there then. We can move it like parametrically there. Let's just do the quicker version of this.
It's also, yeah, well, let's just input that curve in that exact position right there, just so
okay,
persons could see the hiccups that they might face.
Sure. So now we have this toolpath that was there. Where am I working now? Working layer. Okay, that's fine. So let's plug it there. Here we go.
Yep.
You want to run it? You want to see
Sure.
it? Yeah, pretty much nothing works here. Let's play. And so it's trying hard, but not really working in real life.
Yep. So this actually gives us really good insights about what part works and what doesn't, because after a point you see that it's almost like you're really stretching it out, and that's pretty much all it can do and sort of not get to it, which is why you're seeing the tool sort of bounce around our curve quite a bit. But the closer it gets, so this is also a hint to say, okay, maybe this means the furthest it can go is to the edge of the table. But for like the best optimization path, we would normally sort of stick around this region, because that also uses all its axes in a fairly seamless manner.
Exactly. And so let's try to put it there. Too far. That's fair. It's a bit small though.
Yeah, we could scale it up.
Still too far. Let's scale up a little bit more. I don't know, let's see. Let's forget for a second about our, where do we want it in relation to the robot? More left here? Kind of?
Yeah, that looks pretty good.
Okay, we like it. We want to, let's apply, let's stop the loop, let's stop the simulation, exit. Okay, so first of all, let's stop it after the last program position. So we just freeze it to the last one. And you have a better approach to reach to the first point. Actually, let's see the points first. It's always a good way to understand what's going on. Can you email me the file? Yes, Jeff, I'll do that. In my second, I'll do it in a second. Meanwhile, I can.
Sorry, I know you're doing multiple things.
No, that's fine. Give me just 30 seconds. I have, so the file is light and okay, you have it. Okay, so let's zoom back here. Okay, for instance, you might want to, I don't know, to reverse the list of points. So in this case, the 0 is like on the other edge, on the other side of the curve. You may want to shift depending on your geometry. You might want to work on this. Let me plug the list shifted. The point list. Of course, we broke the script here. It's connected to anything. Yeah, let's say that, for instance, 20. What was it? No, let's do 19. I don't remember if it was 20, 21. I don't see the 0 anymore, right?
Right there.
Right, yeah, okay.
go.
So you can just move it around depending really on the result that you want to obtain. Because I remember that, like, some students had the geometry was a closed geometry, but they wanted really a specific point, like let's say a circle, and you can really decide which is the first point. Also because you know that maybe like the robot will stay there a little bit longer, so you have, you know, a stronger effect, stronger light effect there.
Yeah, and also looks like this file is just the right amount of points so that we're not sort of overburdening the script and making it too heavy. So I guess as a general rule of thumb, we could stick with, I don't know how many points we have, but we could go with about like 120 points or right there.
List length. Let's visualize this as well. Yeah.
117. Okay, so yeah, let's make that almost like a thumb rule of some sort. So just so we're keeping it fairly light. And also one thing you notice, if you were to sort of take the exact same curve and so just say, for instance, if this was right there, but just the way we're sort of dividing it right now at these points, if these points were actually to become, instead of 117, if they were to become something closer to 50, you would just see how further away these points were. And then what the robot would try to do is sort of just connect these points. So in a way, it also changes the resolution of your overall geometry, but that's also a good way to sort of bring down the number of points and make it lighter, just in case we're troubleshooting a few of the files. But what do you think of it so far? Have you tried the script yet? Is there anything we could help you with?
And meanwhile, I will export this. And actually, let me put it to the first point as well. That's the way I do that. Should I do that in a different way to get to the
That actually
point 0?
looks pretty good. Yeah.
Perfect. Okay, so let's go to settings, start 0. 0, 0, apply. Let's see, looks good. This rotation. There are a couple of interesting rotations, but that should work. Okay, so let's stop here. I'll export this one as well. We have interpolation. I plug the point to point, so hopefully there will be a smooth light point to point. Saved in my desktop. I apply. Okay, that just appeared. Exit. Okay, I'm sending this to the build lab as well.
All right. Yeah, that sounds great. So while we wait on Jeff to sort of walk us through one of the scripts, we could open up for more questions, or if you guys have started sort of testing out geometries, we could even have you sort of share your screen so the rest of the students could take a quick look and yeah, have a conversation.
Absolutely. So we have the last half an hour. So while we chit chat, we will wait for the.
Oh, also tomorrow we're primarily going to be talking about robotic subtraction techniques. And before I jump into that, I just had a quick question for if you guys have used a CNC milling machine before or know about it, or I'd be happy to sort of start with basic stuff as well. But I was just curious if you guys have had any experience seeing the machine in action. You don't have to have used it. Okay, perfect. So I'll start tomorrow's session with really basic things like what a drill bit is, what are the different kinds of drill bits, and then we could jump into the technical aspect of that.
Let's see a sneak peek. You wanna?
I I have a little
Sure.
question about the file.
Yeah.
Can I share my screen?
Absolutely.
Oh, sure, absolutely.
I can. You have to allow me. Right.
And again, guys, if you want to use OBS Studio and to have everything, actually, I could use them a while.
Can you see it?
Yeah.
Right about here. So here is the toolpad that I made. Is like a go. I have I have
Jeff
right
is
now.
laughing already. He's like, oh my God, we have to process that.
No. It's like I don't know. Let me see right here. Well, to get to 150 is right. So there is a way to, I have here the endpoints to input parametrically the starting point of the toolpath into the settings of the robot. Yesterday you mentioned that, well, I have a little problem here, but in the settings, I can put it right here, start and end point. But I don't know if I can just do it parametrically when I edit my curve.
Well, for starters, since the core component is red, let's try to move your geometry a little bit to see what the problem with the robot is. So as long as that geometry works, then we could dive into
All right.
the start.
Yeah, there's also something weird there that I can't really see. That
Yes.
I'm curious to understand.
Because
Also because like the start and end points, so start point is one point, is literally where you want the toolpath to start. So
this is the preview of the.
Sure. It's also doing something funky right there, just because
yeah,
your geometry, maybe it's too close to what its home position is. So let's try moving that just about like 10 centimeters away. Can we look at this in one of the side views, maybe?
Yes.
but is it one line, like just a continuous
Yes.
line?
It's
Oh, okay,
Yeah,
that's a good start.
it's a closed line.
Okay.
Perfect.
So let me just unpreview. So I have right there the home position, but I
Go to analysis. Okay,
yeah.
so the problem is there. Okay, so one thing that I would do now is to show us the 4 views so that we can really see in space where that object is, because yeah, zoom out. Show us like everything, like the plan view, the front view. Do it in plan from the top. So zoom out a bit.
Maybe it's the
Click.
home
Click.
position.
So the problem is your home position is right here, which is also further into, further into your geometry, and then it sort of goes back. So
let me just move the geometry a little bit further. No, and this with this one.
Oh, okay. You might need more, like a bigger number there.
like somewhere here.
Yeah, exactly. And when you open the graph, click on the red areas.
Right about there, right about there.
And meanwhile, can I pin this to everyone so that meanwhile we can see the window with the robot?
We also
while
have
we're
the
troubleshooting?
toolpath running at the build lab.
Oh, look at that. So meet Bianco in real time, guys. Meanwhile.
Yes, let me like this. No.
So where is the
it
starting
seems
point? Where's the point 0?
here?
In the geometry, I mean. Can you
The
visualize the
starting
point?
point is right about there.
Ah, that guy. Okay. Ah, that's good.
Is the same one, the end point and the starting point. So
Okay.
I don't know.
I
Let me
would put, so drop the list. So connect your geometry to the list. So, and visualize the point, the number of the points. And we want to put the 0 there.
right. Let me just, because I have right here.
Now the robot is in the dark.
Here I have, I don't know, like so. So
That's
there,
nice.
4, 6, 8. Like this is the, let's see if, no, I don't know. I don't know, guys. What could be wrong here?
Actually, just for the sake of troubleshooting, is there a way you could bake this object for us and then we input that as the curve? Just
All right.
to check if it's a geometry or if it's a start point, because we're also sort of seeing
Here,
a few
the,
hiccups
you
right
can
there.
see
Exactly.
here that the robot turned red. I don't know why, but let me bake it. Bake.
You need to control the numbers.
So let me just preview, and then so is right about here that well, I will give it a look by myself. I think it's just there.
How about we rotate your geometry a little in that direction? Because what you're asking the robot to do is go straight from a point to a certain point, but to get to that second point, it has to pull a weird dynamic with 2 of its axes. That's why this and this one is going red.
I know how that is. All right. So now I think it works.
All right. Yeah, that looks a lot better. And let's see how many points you have there.
I have 80 right now. Let me view one.
Just have running slow, so there's something wrong.
At the end of the script is a weird movement too.
Yes, because there's also to sometimes what the robot has to do is move a lot of axes just to get from one point to another. So a way to sort of avoid this would be if we move it in space a little, just a little bit down. So right about there would be a good position. But since the script works, it's just a matter of tool pathing it, but your geometry looks all clean to me. There we go. Nope, just
Right.
all right. Yeah, let's give that another shot.
Now I think it turned red right there.
I think it's the curves right here which are.
I think it's the home position. The home position.
This geometry changes too soon and slightly drastically. Just the way we're trying to twist and turn. Hang on. Okay, this seems to be working.
Yes.
Can we see the analysis window? All right. So one thing when we're doing these, if we see the red and green lines so relatively mirror one another, if we see any long or steep slopes of those two axes going against one another, it might cause an error, might not, when we're running the script, because it creates a fast motion as the two axes twist against one another. We can try a script if it looks good like this, but just for everybody in general, I wanted to say, like, as you're looking at things, if you see the red and green lines, let's say, go all the way from the top to all the way to the bottom, kind of against one another, that might be a bad sign as far as the file being able to run on the robot. Also, anything that goes, I'd say above 250 on the graph will probably go out of bounds for one of the axes. I think the limit is actually like 275, but that's the maximum rotation of the axis, a given axis in one direction. And not all axes can go that far, right? So for 5, axis 5 can only go approximately the angle of a wrist, right, in either direction, whereas axis number 6 can rotate almost all the way around in both directions. So those are some things to think about as you're looking at the analysis window.
And thanks a lot. And sorry, I hear myself. I don't know if I have anything open here, but can we spend the last like 4 minutes like with you, Jeff, navigating us in the build lab and show us how you run the script, and if you could run that again for us, and I will pin you for everyone.
Okay, sure. All right. You'll have to tell me if you can see this or not.
Yep.
I don't know how I'm going to actually use this thing. Hold on. I have
no
no
it's okay.
eye.
It's okay. Just tell us. There's no need to. I mean, you guys know that we can apply the script there.
Can you read it okay? All right. So
Yep.
so I'm going to reset the program, and it's running some version of Windows on here. There's no mouse or anything like that, so most of the controls are with menu buttons on the top. So the first thing I did was I reset the program. So here you can see the lines of script. The first thing is to go to the initial position, and I have it in auto mode, which means it's going to run the script all the way through if I press the start button. To begin with, though, I need to go to the start position, and I'll hold on to this green button, and I'm going to move the pendant so you can see the robot moving. So right now I'm just holding the green button and it's going to the home position somewhat slowly. I'm going to speed it up a little bit. All right, so there's our home position or start position. Okay, so at this point, since I'm in auto mode, if I just press the green button, it'll run the script. There's some other options. I can go step by step. You can see this little character there going. It would go one line at a time, so it would increment each individual point and then stop, and then you could advance it. But we're going to run it all the way through just by pressing the green button. So, and I'm going to hold the pendant up so you can see, I think, the program running and each line being highlighted as it moves through. And there's a robot. Doing its dance. If we need to stop it at any time, there's a stop button. There's also a speed control here, so let me get it going again. Right now it's at 100% speed, but I can slow it down to, where am I at, 10% speed now? Or I can speed it back up to 100% speed. And it's still going to continue running through the program. So what I was saying about the axis 4 and 6 on the graph, sometimes we can get through a really fast rotation by slowing the machine down, like right at the key moment, by paying attention to what line it's on. So let's say there's going to be a fast spin at line 59 or 56, 60. I might slow it down, pass through that point, and then speed it back up again in order to get the code to run successfully. Anyway, so here we're at the end of the program, and I'll just back out of the this view. So I'm going to cancel program. I'll come back to the file browser. So this is the file browsing system. We have in this folder the script for doing the maze. Let's open that one. And I'm going to go to the start position on this one. So this will be kind of interesting. So if you think about the two different end effectors, one is pointing down and, oh wait, I shouldn't do this. This would be bad, I shouldn't do this. Okay, I was going to say I should run this script and kind of draw the flashlight through the maze, and that would look really cool. But I noticed earlier that the planes that were used to construct the maze are different from the planes that were used to do the LightBright assignment. I don't know if you're paying close attention to the orientation of those planes, but one was straight down, and the LightBright attachment treats the planes approaching it from the side, right? So if I ran that script right now, basically, even though the end effector looks the same, it's basically just a pointy thing, it would come down and it would try to do the maze in this orientation, and that would cause a collision with the platform. So I'm not going to do that.
That's awesome. You want to run it one last time, and then we ask the students if they have any questions, or if I think that's great. I think it clarifies the workflow.
Yep. Yeah, for sure. Or also, maybe it's a good exercise to just use your maze toolpath with this script first to see how different it would look. And as soon as we plug it into our newer script, which in a way sort of orients the planes not in X and Y, but instead vertically, that's when it would start to make more sense. But I think one hiccup that is most commonly seen is also the fact that you see the robot sort of turning red, like we saw in one of the student scripts. But a good way to fix that is to move your geometry, scale it a little, and put it in a good enough position where you think would be reachable at all points.
That looks great. So do you guys feel that you have a better understanding of, the stream from Grasshopper and Kuka PRC to the robot? Jeff, that was super, super helpful. Thanks
Absolutely.
a lot
Thank you so much.
for the demo. And yeah, so you're seeing the kinematic, you're seeing the toolpath. You can recognize the form, right, that we designed earlier in Grasshopper, and taking a long exposure picture, you will keep track of all the positions of the robot and all the target points that it will reach. So hopefully this is more explicit, it's more clear. And what else? I think we did it. We made it through the session.
Yep.
As Misri mentioned, tomorrow we'll talk about subtraction and CNC milling and robot milling. And I see some thumbs up. That's great. Hopefully you guys enjoyed this session. And what else do we need to cover? Anything? Do remember, like, share both Rhino and Grasshopper so that we can just fasten the process of troubleshooting, and drop on the Google Slides file the documentation. So the digital twin, the robot, some diagrams, show us the toolpath, and in a way that we can understand the three-dimensionality of it. So, okay,
yeah, no,
guys.
it's been a very fruitful and a productive session. So yeah, just feel free to explore some geometries. And even if you do see hiccups and through the process of changing the geometry or changing the position or changing the scale, if you sort of get over that hurdle, it's also good to share that with your peers, because I'm sure we'll be encountering that quite a bit. But yeah, just feel free to reach out if you have any problems.
Yeah, we're looking forward to seeing the geometries and to seeing, the photos by the end of the workshop. So, more comments, Jeff? We good?
I think for now we're good.
Awesome. So we'll see you guys tomorrow, and do good work. Yeah, let us know if you have any comments, questions. We're here to help you guys. So have a great day, or afternoon, or night.
Thank you so much. It's been a pleasure.
Bye,
All
guys.
right, we see you guys tomorrow. See ya. Ciao.
Cheers.
Ciao.